method, but for the moment, Cyril will just tell you the method that he developed. And so, but it is available as part of the MS-DOTS implementation.
So thank you for the introduction. Okay, so in my presentation today, so I'll start by reviewing a little bit the definitions of the LOB, LOD, and then LOQ, and then I'll introduce the R package that we developed just to implement the method. So the first thing you have to do is build a calibration curve. So basically, you spike. You measure the intensity of spikes with known concentration, and you get this curve here. This is kind of like the canonical response curve that you would observe if you had low enough concentration spikes and very high concentration spikes. Very often, you only observe the linear part, so read this region here. But if you actually do get measurements in this range, or it doesn't happen very often in the saturation regime, it does complicate things for the LOD. Okay, so this is supposed to read LOB, LOD, LOQ definition. So in this talk, I'm only going to talk about methods that are based on a curve fit, so not methods that are just based on the blank sample, for instance. So this is the article that we just talked about, this, which is, I think, today like kind of the most used method. So you can also find a very good presentation in this sort of review article here, and then it's also discussed here. Okay, so now how to define the LOB and LOD. So I'll talk about the LOQ later. So you can really define kind of pretty rigorously the LOB, which is the limit of blank. So basically, it's the minimum concentration above which the false positive rate is less than a given tolerance alpha. So alpha, as was mentioned before, alpha is usually 5%. And then the LOD is the minimum concentration above which we have a false negative less than 5%, and also a false positive less than 5%. So if you look at the calibration curve, so this part was actually shown before too. So you basically have the LOB here, where this is the upper bound for the noise. You get this area here, which is 5% of the normal distribution. And then at the LOD, you have 5% above and then 5% below. So for the LOQ, there's not a really nice statistical definition, or at least a very nice rigorous statistical definition. It really depends kind of on like what people in your community do. A lot of people use a CV value, CV, which is mean over the standard deviation, less than 0.2. You can also use the recovery factor. So basically, this is the deviation from the linear response. There's also, as was mentioned before, some methods that are just based on the blank sample. But the LOQ really depends on your specific application. Okay, so in terms of the response curves, how do you kind of practically measure the LOB and LOD? So basically, you need to have an estimate for the upper limit of the noise, which, well, for this specific response curve, it's very easy to get, because you really have a very nice measure of the noise at low concentrations. And then you have to find the intersection between the response curve and then this upper bound for the noise. This gives you the LOB. And then you need to estimate the prediction interval of the response. So basically, you'll usually do that by resampling the data. And then so this gives you the orange area here. And then you take the intersection between the lower bound of this prediction interval and then the upper limit of the noise again. And then this gives you the LOD. And then for the LOQ, I mean, you can't find it like that. You have to use some other definition. So practically speaking, when you run an experiment, so what do you do? Something which I'm not going to talk about, which is actually very important. So Sue talked quite extensively about that. You have to normalize your data somehow. So ideally, you have, for instance, heavy peptides. And so that's something which, of course, you have to do before you start calculating the LOD or LOB. And then you have to do a curve fit. So basically, so how do you come up with this curve fit here? So before this was always a straight line, and then so we'll see in the method that I'm introducing, this is not going to be a straight line. And then just because you have to find the intersection between this calibration curve and then the upper limit of the noise, you need to also come up with an estimate of this upper limit of the noise. And then at the end, you just take the intersection between the two. So I'll start by showing just a very basic example. So this comes from the CPTAC 7 study. So I'll talk about where you can get this data online afterwards. So here you see that you have a very nice linear response. So this is kind of like the overall view for all the concentration spikes between 0 and 500. And so if you zoom into this area, so for the low concentrations, you see that the data is very clearly linear. So this works really well. Something you do have to account for to estimate the prediction interval, so this shaded area here, is that you have kind of unequal variance between the different spikes. So you can account for that by doing a weighted linear fit, which is just a little bit more complicated than a regular linear fit. And then you can estimate this. There's either a closed form formula that was shown before, or you can also just do a bootstrap. So basically, we sample the data to get an estimate for this prediction interval. So this is kind of like the ideal case where everything works well. But so here is another case. So this comes from another data set. I'll talk about the different data sets that I'm using a little bit later. So here you see that we're using a linear fit. But at low concentration, there's kind of something wrong just because, well, the linear fit doesn't fit the data very well here. It does at high concentration where the response is linear, but at low concentration, the response is not linear. So you can clearly see that, well, I mean, just by looking at the fit itself, it's a linear fit is really not the way to go. So, well, a lot of people have noticed that before. This really happens when you have some low concentration spikes, when you actually capture this regime here. So, for instance, if you didn't have any spikes in that region, a linear fit would be probably like the best you could do. So there's been a number of methods that have been introduced over the years to deal with that nonlinearity, so that threshold at low concentrations. So this is an article from 2015 that proposes a method for that, and this is like an older article that basically, so they're both actually based on a logistic model, which is so this is called a logistic curve. So basically, it's just a curve that basically has a nice threshold at low concentration. So these two methods actually work pretty well. They do work a lot better than the linear fit at low concentrations. But there's kind of a number of issues with them that I'm not going to discuss today. We have currently a paper that we're working on that kind of compares the method we're proposing with these methods, and it shows that the method we're proposing is more robust and avoids some problems due to overfitting. But I'm not going to discuss this here. I'm just going to contrast the linear method with the method we're proposing. So this is for the same peptide that I showed before. So this is the response curve calculated, estimated by this new method, and then you have the LOB. This is the wrong color. The LOB and then LOD here, and you see that we do indeed capture this threshold at low concentrations. So you can, as I mentioned before, you can actually show that this method is better than the logistic regression. So what exactly is this method? So it's basically based, so I'm not going to really discuss kind of the technical details of the method here, but it's basically based on a resampling of the data. And we either fit a straight line, so just like we do for a linear fit, or an elbow function, which is visible here, so it goes like this, it's flat, and then it goes up just like an elbow for with a straight line. And so depending on the data that we resample, we either fit this straight line or this elbow function. And then in the end, we just average all the fits that we get, and then we get a mean fit in red here, which is the calibration curve. And then so you see here that we really capture this threshold well at low concentration, and then we really get a linear response at high concentration. The nice thing about this method is that if the data is linear, the mean fit will be completely linear, which is a huge advantage of this method. Okay, so now I'm just going to talk a little bit about the different data sets that I mentioned before. So online, there's a very nice repository that we actually talked about yesterday and today, which is Panorama, and on which you can find data from a lot of previous CP-TAC studies. So there's something like 10 here. There's actually many more data sets than those, because each actually contains multiple data sets. And so these are really data sets with that are really designed to calculate. They're really calibration studies, so they're kind of perfect to test the new method that we're proposing. So here, what I showed is the ratio of the LOB and LOD obtained with the new method, and I divide this new value of the LOB and LOD by what we obtain with a linear method. So you really see that with a linear method, you really tend to underestimate the value of the LOB and LOD. And you can kind of understand that because a linear method will always fall like this. It will always go over the threshold. So you'll just have an LOB and LOD that are too low, which is kind of like the worst case scenario, because you really do not want to underestimate these two values. So now I'll say a few words about the R package where the new method is implemented. So I'm only going to go kind of very briefly over this, because a lot of people don't really know R very well. So you can find like a lot more information about how to use the package online. So this is the address, and then you have a tab just for the LOB and LOD method, and there's multiple example data sets and kind of an R document that gives you examples of how you can use this new method. So I'm just going to show a quick example. So basically, this is the input for the R function. So it's basically the data which is plotted here. So basically, you have the intensity here, for different concentrations, and there's 4 replicants here. So this is kind of like what we saw before with Quasar and then in the Excel file. So this is the input, and now I'll start by presenting what happens with the linear method. So I also implemented a linear method, so the limit method that we discussed about before. So the function for this is called linear quant lim. You can find a lot more information on the website, and if you do the help function of R. And so basically, if you, for the data that I showed previously, if you just run this function, this is kind of the output that you get. So you get both the curve, and then, so there's also the value of the slope and then the intercept, which I'm not showing here, and then the LOB and LOD here. So this is the linear function. So part of the reason I implemented that was to really compare the new method with the linear method. And also just because there's not many R packages that actually calculate the LOB and LOD. So it was kind of a nice contribution to. So this is for a different data set. So the data set that so for this peptide, you really get a linear response. So this is really, it's really appropriate to use the linear method, as opposed to for this other peptide where you really get a threshold at low concentrations here. And so the method that we're proposing is implemented in this other function called nonlinear lim. And basically, this is the output of the function, so the value of the LOB and LOD, and then also the fit. So this is just a comparison of what happens for the peptide that I just showed between the linear and nonlinear method. So you really see that with the linear method, you'll tend to underestimate the value of the LOB and LOD just because of the kind of like basic geometry of the fit. So yeah, so just don't hesitate to just contact me or just come and see me if you're interested in using this package, because I only went over it like very, very fast now. So if you have any questions.
I can attest that Cyril is very responsive by email when you have questions about his function. And if I'm not mistaken, Cyril, it's always good to have access to interesting data sets?
Yes, absolutely, because I really so tested this method with a lot of maybe something like 2,500 peptides, and it was really great to kind of debug the method, because there's a lot of peptides that are not great, but you still have to get a value for the LOB and LOD for those. So yeah, the repository online was very useful for that, and just to really cover like all the different cases.
And so when you use this in MS Stats, what kind of readout do you get aside from the plots? Do you have LOD calculation and LOB calculation? Like, can you
yes. So you get basically the output of this function, for instance. Well, this function is
right at the top.
yeah. So at the top, you get the value of the LOB, the value of the LOD. You also get the value of the slope and then the intercept if you remove all points below the LOB, below the LOD. So it gives you like the true value of the slope and intercept here. And then you also get the just because it's also a non-parametric method. So this curve here, there's no closed form expression for it. So you also get basically the value of this as a function of the concentration. So you can plot it again.
So I think at this point we are at the 5 o'clock, just about the 5 o'clock hour. And I am forgetting what was on the agenda. I think it's just work on your own stuff. If you have questions, we'll be here until 6. If you want to practice anything, there are extra files on the Skyline USB drive, and I can walk you through pasting peptide sequences in, importing a FASTA file, digesting. If your brain needs to just take a break, that's cool too.
And just so, I'll be back at 8 o'clock in the morning.